Hi everyone, welcome to Unit 2 of Multivariable Calculus. In today's video we want to cover vector functions. So we want to introduce vector functions, introduce the notion of a vector function. Now sometimes in Calculus BC they throw this idea in there with parametric and polar coordinates. Vector functions are essentially glorified parametric equations, as I like to think about them, but we really need to think about them as vectors. So they're vector-valued functions, essentially. So basically, at each point along a curve, you're defined by some magnitude. That magnitude could be direction, but anyways, or that magnitude could be velocity, but anyways, as I move along a curve, my speed could change. So along curves, things can change, so you can kind of see where this is going. It was very similar to the idea that an object can move at different velocities down a parametric equation in such a way that taking the derivative of one of these things is not necessarily finding its exact slope, but finding the rate at which t changes, the rate at which our object moving along the plane changes, not necessarily the slope of the curve, which might just be its direction, right? I might not want to know. I might not care about the slope of the mountain that I'm climbing, but I would care about the speed that I'm climbing up the mountain. Do you know dy dx would be the slope of the mountain, and the actual velocity would be something very different. Anyways, I'm getting a little bit ahead of myself. We'll discuss that in due time. Let's discuss the notion of a vector function first. Now, the idea of a vector function is very easy. It's very similar to what we've discussed in the previous unit. But essentially, a vector function is a function such that if I have an n-dimensional vector function, so let's say I have r to the n of t, well then that's going to be equal to r sub 1 all the way over to r sub n, or we just have tons of components. But the three-dimensional case, we have three components. So we have three-component vectors describing the motion of our vector function. Now the vector function would be defined when all of these three components are defined. So f of t could equal secant squared of t, or something like that. You need to know the domain of secant squared of t, because otherwise our vector function wouldn't be valid, even if g of t and h of t were like x and 1, or t and 1, and they were defined. Even if one component is undefined, then the whole thing will be undefined. So the vector function is defined when all of the three components are defined. So for the domain of a vector function, that's important to think about. Let's just do a couple of examples. This is a very easy concept, and I don't think we need to spend too much time thinking about it. So I would like us to sketch r of t equals cosine of t and sine of t. Now we can turn this into a set of parametric equations. Notice how I haven't put any restrictions on t, because we don't really need to worry about that. First of all, from x and y, we can see we have cosine of t and sine of t. And if you remember from single variable calculus, that's the parameterization for a unit circle. And then we also have z equals t. So we have x squared plus y squared equals 1 for all t. So we know that a level curve for the xy picture is going to look like the unit circle. Right? Okay, and we know that for the typical parameterization for x of t and y of t, we move around in the counterclockwise direction, right? Now we also have z of t equals t, so when we project this into the xyz picture, we're going to be moving up, but we're going to be moving up in a counterclockwise direction because of the way that the parameterization for x and y works for the parameterization of the unit circle. So we're going to be going upwards at a rate of t around the unit circle. So it's going to look like this helical kind of shape, right? So we start, and if I were to look at this from a bird's eye view, I'd get this unit circle. But essentially, we start up, then we rotate around the z-axis. We continue to rotate around the z-axis again. And we make one full circle, and then we keep on going. It's kind of like a strand of RNA, I suppose, because RNA is single-stranded, so you only need one of them. I'm not sure if they form a helix, though. All right, I didn't do well in biology, so that's fine. We'll just discuss the math here. All right, anyways, why don't we just do another example? So for this time, I would like us to find the vector function modeling the intersection between the unit cylinder. So the unit cylinder, by the way, is x squared plus y squared equals 1, because that forms the cylinder up here. And the plane y plus z equals 2. Now, if you notice here, we have our plane, and I like how I set this up with Apple Grapher, so it shows the height with color. I think that's fairly cool. But anyways, we want to find this little guy up in here, and we want to find that parameterization for that. Okay, so we have x squared plus y squared equals 1, so that should immediately tell us that our xy parameterization should be a unit circle, because that's the unit cylinder. So the only thing that's going to be skewed is going to be the z. So we get x equals cosine of t and y equals sine of t for t equals 0 to 2 pi, because we're doing one full rotation. So we can plug this into our plane equation, y plus z equals 2. So we get sine of t plus z equals 2. Then we can solve for z. Then z is equal to 2 minus sine of t. Now we can plug this into our final parameterization such that x is equal to cosine of t, y is equal to sine of t, and z is equal to 2 minus sine of t. And finally, we can create our vector function such that our vector of t is equal to cosine of t, sine of t, and 2 minus sine of t. All right. Thank you for watching our video on introduction to vector functions. In the next video, we're going to be talking about limits and continuity of vector functions. And then we'll be talking about derivatives and integrals of vector functions, and then we'll look at the arc length, and then we'll discuss the applications of the vector functions to physics. So that's what we have for Unit 2, pretty much. Thanks for watching, and we will see you next time.